So who has heard of Azul? Okay, right. So there's a quick thing about Azul, because I'm the deputy CTO at Azul. What we do is Java. We do Java runtimes. We don't do Java programming. We do the runtime that you execute your applications on. So that falls in two parts. One is our straight build of OpenJDK, which is a replacement for Oracle or Temurin or Corretto. And we have a high-performance JVM called Prime. And that's more what I'm talking about in this presentation, is how we can address the issues of Warmup. So, first thing we need to look at is what actually happens when we start up a Java application. And that can be divided, as you can see in the diagram, into a number of stages. The first of those stages is the startup of the JVM itself. JVM is an executable. So we need to start that up. That's going to load code, it's going to start executing and doing things. So we need to load and execute that code, and one of the things that happens every time you start up a JVM is that it will generate a set of templates for each of the bytecodes that we have in the JVM instruction set. Now you might think, well, that's a lot of work, but it actually happens really, really quickly, because those templates are effectively a set of native instructions which translate those bytecodes into whatever the platform you're running on to do the work. The reason it does that every single time is because when you start it up on a different machine, there may be additional instructions that are available, and so it can take advantage of those to give you slightly better performance. Not really much, but that's essentially what happens when you start up the JVM. So that starts up the JVM, and then we need to start up our application. To do that, we use the classes which make up the application you've created. What we'll do is we'll load those classes, take the bytecodes, we'll verify them to make sure that the sequence of instructions doesn't break any of the rules which we have in terms of the JVM, so that you can't try and break into the application, the JVM, and so on. We'll also initialize some of those classes. And the JVM uses lazy initialization. So even though it loads classes, it doesn't necessarily initialize them at the same time. And then once we've loaded our classes and we've initialized which ones we need straight away, we'll start doing some application-specific initialization. We'll execute your main method and whatever you need to do in terms of setting up your application, whether it's opening JDBC connections, whether it's network connections, whatever, then that's going to happen as application-specific code. Then we go through the process of application warm-up. And this is where we're actually running your application code using the bytecodes that you have. And rather than just executing them interpreted using those templates, what we're going to do is we're going to identify sections of code or methods which are used frequently. And when we find one that's used frequently, we do just-in-time compilation, which says take that method and those bytecodes, put it through a compiler, and generate a set of complete native instructions to give you better performance. And that actually happens in a couple of phases. So there's more than one JIT compiler in the JVM, as we'll see. And then obviously, as that's happening, you're doing the specific work for your application. So three distinct phases. And if we look at those in a bit more detail in terms of speed, what we'll say is that the time to actually do the first operation of your application, so your first transaction, is a combination of getting the JVM loaded and then getting your application loaded so that you get to where you can actually do some real work. And then the time it takes to complete N operations is how long it takes to get to the first operation plus how long it takes to complete those N operations. So there's a sort of fixed amount of time plus however much time you need to do what you're trying to do in your application. If we look at how quickly these things happen, actually loading the JVM is very fast. It's just an application. It's not a particularly big application. So we can load that very, very quickly. And as I said, generating templates, it happens in the blink of an eye. Application startup is quick. Loading application classes doesn't take very long. Initialization is quick. Maybe it could take some time to do your application-specific initialization, depending on how much work you have to do. But typically what we're saying here is that's going to happen pretty quickly. So your timed first operation isn't too bad. But then what we see in terms of that warm-up time, how long it takes to compile all the frequently used code and get to your optimum level of performance, that can take a long time. And by a long time, it could be a few minutes, it could be a few hours, literally it could be a day, depending on what your application does. Now, if we look at what's actually happening here, as I say, class files contain bytecodes. Bytecodes are the instructions of our virtual machine. So they don't necessarily translate one-to-one into the instructions of whatever hardware we're using at that time. Now, initially, when we start running a class and execute methods, we're going to do interpretation of those bytecodes. Each bytecode is taken and it's using that template converted to a set of native instructions which are executed on the CPU, and then we move on to the next one. The only optimization that happens at that point is that there are a couple of examples where certain pairs of bytecodes happen together very, very frequently. So when you look at the templates that are created, there's a template for each virtual machine instruction, plus there's a couple of ones which are pairs of instructions that happen frequently together. But that really is the only optimization that happens there. As we identify the frequently used methods, we count how many times a method is called, we hit a certain threshold, and then we use this just-in-time compilation, which uses two different compilers. So the first of those is the very imaginatively named C1. And what C1 does is compile that method very quickly so that we can generate some native instructions ready to use. But what it doesn't do is apply a lot of optimizations. It's all about getting that code generated quickly. Once we've done that, we then run that method using the natively compiled code, but we also profile it at the same time to understand how that code is actually being used. When we hit a second threshold to say that this method is a really heavily used method, then we pass it to the, again, imaginatively named C2 JIT compiler. What C2 will do is it will say, right, let's recompile that method, but using the profiling information that we've gathered along the way to understand how to optimize it much more heavily. And that gives us much better performance for that method. Once we've done that, we can then run, and as we compile more of our methods by C2, then we'll get to the point where we've got our warmed up application. So warmed up means all the frequently used methods have been compiled using C2. So the problem with this is that we do this every time we start an application. We start an application, goes through this process of identifying methods, compiling them with C1, profiling, compile with C2. Start the same application again, and you're going to do exactly the same thing. Identify the frequently used methods, compile with C1, recompile with C2 based on profiling. So that's wasteful. What can we do to get around that? And so if we look at a graph of a typical type of application, this is what we're going to see in terms of performance. The kind of yellow, kind of looks yellow, the yellow bit on the bottom there, that's where we're doing interpreted mode, and that tends to be very slow. Then we get into what should be green, but looks slightly less yellow, is where we're doing C1 compiled code. So it runs a bit faster, but we're not getting that heavy optimization. And then the blue sections that we see there, that's all about where we've compiled into C2 and we're getting heavily optimized code. And eventually we get to that steady state on the right where we've compiled all our frequently used methods. We call this the application warm-up time. How long does it take to get to that steady state of optimized code?
Yeah, on the graph, what's the x-axis and what's the y-axis? I'm sorry.
Okay, so the y-axis is performance, so how much performance you're getting from your application, and then the x-axis is time.
Okay, so what unit is that?
Sorry?
What unit is that?
How?
What unit?
Oh, what unit? Oh, forget about what unit is, because this is just a sort of the idea of what an application will look like. It doesn't really matter what the time. It could be minutes, it could be hours. It depends on the application. Because very much it depends on how frequently you use methods, how many methods you use, what your application does. So this is a very important thing, you see, because all applications are different. So we couldn't give you a graph which shows how every application works. This is just a generic type of graph of how an application will look. But you don't really need to think about the scale of the graph.
Can I ask a question?
Sure.
So what are some of the indications that we have a properly warmed application? Is it memory stabilization? Is it, what are some of the
Yeah, so the thing that you'll see is the level of performance. So how many, let's say, transactions per second. So when you get to a steady state in terms of how many transactions per second you can deal with, that's going to give you an idea of what your sort of, when you warmed up, because you set it, you get to a level where you're seeing, let's say, 1,000 transactions per second, and that's consistent, versus when you start up, you get maybe 200 transactions per second. And when you see that 1,000 transactions per second, that's when you know you got warmed up. So as I say, the problem we see is that if we take that graph, when we run our application, that's what we're going to see. When we run the application a second time, we see exactly the same thing as we saw before. And if we run it a third time. And this becomes much more of an issue when we're dealing with things like microservices, where you want to be able to spin up new instances of a microservice to address changes in load. You're going to see this all the time. So you have this warm-up problem that you need to address. What we'd really like to see is that we run the application once, we let it warm up, we get it to a point where we've got a steady state number of transactions per second, and then when we run it a second time, we start from the same point. So we've already got the code, we know what we're doing, and we continue running. And when we run it again, we get the same thing. So this is what we'd really like to see. And what I'm going to talk about now is how we can approach that. What can we do to change from 3 different graphs where they're exactly the same and we go through the warm-up to this sort of situation. So the first solution we could try is ahead-of-time compilation. When Java first came out and it only used interpreted code, didn't have JIT compilation in the very beginning, it was criticized for being much slower than natively compiled C or C++, which it was. And the solution that most people, when I spoke to people about this, said was, why don't we just compile it like we do C? Just use a static compiler and compile it into native code. And that's definitely a possibility, because you can write a compiler that takes Java, it's just a high-level language, you can generate intermediate representation, you can pass it through a back-end of a compiler, and you can generate native application. And so that's what you can do. So you do ahead-of-time static compilation. You don't have to interpret bytecodes, so there is no warm-up associated with that. There's no analysis of hotspots. You don't have to identify the methods that you have. You don't have to do runtime compilation. And one of the drawbacks of runtime compilation is, of course, you're now sharing the CPU resources and the memory resources that you have between doing application work and compiling your code at the same time. So you're reducing the throughput of your application whilst you're doing that warm-up, because you're compiling code. You start at full speed straight away, because you get immediately full performance because everything is compiled into native instructions. This is the Graal native image approach. Who's tried Graal native image? Oh, fewer people than I would expect. Interesting. Okay, so Graal native image is a project that was started at Oracle. Actually, it was started at Sun before that. But it's the idea of taking a Java application and rather than converting it into bytecodes through Java C, you actually convert it into a native application. And you run it just as you would compiled C or C++ code. So we've solved our problem. That's it. End of presentation. After only 15 minutes, I've done everything. Haha. Except not so fast. Yes, and I mean that in 2 different ways. So ahead-of-time compilation is, by its very definition, static. It does not change. So once we've compiled our code, we have a fixed set of paths through our code. The code is compiled before it's run, very logically, ahead of time. So we compile it before we do any execution of the code. And what that means is that the compiler doesn't know what that code is actually going to do as it's running. So it knows, it can analyze the code, it can look at the structure of the code, and it can compile based on optimizations. There's different techniques that you can use in terms of things like escape analysis, loop unrolling, all sorts of standard techniques that you can use. But it doesn't know what's actually going to happen when the code runs. Now, there is a way of improving that, and this is something that's been around really since the beginning of compilers, which is called profile-guided optimization. What you do is you compile your code statically, you run it, but as you run it the first time, you profile it to see how it works when it's running. And then you take that profile and you feed it back into the compiler, recompile with that information to generate code which is more optimized based on what the code is doing when you run it. So that gives you an improvement in the level of performance. But that only helps partially. Let's look at what we can do if we're using just-in-time compilation. And this is what we call speculative optimizations. Speculative optimizations essentially say we look at how code is running, and when we try to compile a method, we say, let's assume that the code is continuing to run in exactly the same way. So we'll optimize based on that assumption. Now, there's a couple of examples I can give you of this. So the first of those is what we call inlining of monomorphic sites. I have a simple class here called animal. We're using an encapsulation of a property called color. So we make it private, so we can't access it directly. We then have an accessor method for that in order to get the color. So method getColor returns the color. Very simple. Now, if we want to use that in our code, we say myColor equals animal, the reference to the object, getColor, call the method on it, which gives us back the color. Fine. Now, in terms of the way that code is going to work, is because we're calling a method, if we compile that directly, what's going to happen is we have to create a new stack frame, push that onto the stack in order to call the getColor method. All that's going to do is get the value of the color and return it, and then we pop the stack frame off again. So that's very inefficient because we're creating a stack frame and removing a stack frame simply to access that variable. What the compiler will do is it will say, okay, I'm going to be a little bit clever. I can still respect the contract in terms of what code you've written, but I will, rather than treat the color as being private, I'll treat it as public. So that when you call that method, rather than having to actually make the call to the method and create the stack frame, I'll simply access that variable and give you the value back. And it can do that because nothing clever is happening in terms of that accessor method. It's just returning the color. So all we do is change that code to be animal.color, and it works. But in terms of compiling that, we can do that with a just-in-time compiler. If we do that with a ahead-of-time compilation, we run into the problem that Java is a dynamic language from the point of view of class loading. So we could end up with a situation where we had a different implementation of that method. And so the compiler can't actually do as much method inlining if we do static compilation. With just-in-time compilation, because we know exactly what is going on at any time, we can guarantee that this is going to work. It only works if we can do where we have the situation there's one implementation of getColor. A second, slightly more complex example is branch analysis. Here what we're doing is we're saying, okay, I've got a slightly contrived method, which is called compute magnitude. It takes a value as a parameter, and then we test that value to see if it's greater than 9. If it is, we call another method called compute bias to calculate what the bias is we want to use. If it isn't greater than 9, we return 1. So we set bias to be 1. And then we return the log base 10 of bias plus 99. Right. Now, what we can do in terms of branch analysis is profile that method as it's being used. And we can count how many times we go through the true branch and how many times we go through the false branch. When we come to compile this code, we can look at that value and we can make an assumption. So let's assume that we never go through the true branch. In that case, we can actually modify that code quite significantly to give us better performance. So now what we'll do is we say compute magnitude is going to be compiled like this. We'll say if value is greater than 9, because we still have to deal with that situation, because although we assume it's not going to be greater than 9, there may be a situation where that occurs. If that does, then we call this thing called uncommon trap. Uncommon trap is where we call a de-optimization. We've made an assumption about how the code works. We've compiled it based on that assumption. But if that assumption then breaks, we have to throw away that code and recompile based on how the code looked before. So we need to recompile that code. But if we don't have that situation, we can simplify our code quite a lot because we can say, well, bias is set to 1, 1 plus 99 is 100, log base 10 of 100 is 2, so it's a fixed value for everything. So let's just return 2 rather than doing all that calculation. And that will give us significantly better performance than having to do all that work. And this is just a couple of examples of how we can do this. There's lots of this that happens in terms of the way the JIT compiler works. So as I say, the thing we don't want to see is a de-optimization, because we effectively compile code that we have to throw away and then recompile it.
Why would you have to de-optimize?
Right. So you'd have a de-optimization if somebody calls that method with a value of 10. Because if they call that method with a value of 10, then suddenly you need to go back to the previous code and you say, okay, we've got a value greater than 9, so we have to then call compute bias with that value. But in our modified code, we don't do that because we're assuming that the value is always is never greater than 9, so we can get away with bias always being 1. Does that make sense? So what we've done at Azul is we use a lot of speculative optimizations in our JIT compiler. And what we found is that more than 50% of the performance gains we get is from speculative optimizations. The fact that we can change code as it's running and base our compilation on how code has run up to this point. That only works so long as we can de-optimize as well as optimize. Because if we can't de-optimize, we end up with a situation where we're not compiling the right code. De-optimizations are very bad for performance, so what we really want to do is avoid them as much as possible. Because if we de-optimize, we're throwing away code we've already compiled, we've then got to reuse the CPU again, we're going to compile that code again, bigger the method, the longer that takes, and so on. So if we compare AOT versus JIT compilation. So AOT, class loading, prevents method inlining, as I said. We can't do runtime bytecode generation because we've already got our fixed set of instructions. Reflection can be done, but it's complicated. You basically have to declare everything that you want to do reflection on before you start running or compiling your application. You can't use speculative optimizations. Technically, you could sort of do that, but you'd have to have multiple different compilation units for different methods and then have a branch based on which version you wanted to use. It's nothing, I've never seen anybody use that because it's so complicated. Overall performance will be typically lower. That's not a completely definitive thing. Typically, you will see lower performance than JIT compilation. But you do get full speed right from the very start, and you don't have the overhead of having to use the CPU to do compilation whilst you're running your application. JIT is basically the opposite of all of that because you can use aggressive method inlining. You know exactly what method's being called at any given point. You can use runtime bytecode generation because you're using bytecodes. Reflection is, and I say relatively simple because reflection I don't think is ever truly simple. You can use speculative optimizations because we are compiling whilst it's running, and the overall performance will typically be higher. Not guaranteed, but typically will be higher. But it does require warm-up time, and it requires the use of the CPU. So again, if we come back to our graph, this is where we're using JIT compile code. This is the sort of performance level that we're going to see. If we compare that with static ahead of time compiled code, we're going to see this sort of profile. So although we accelerate much more quickly, we get to our optimum level of performance straight away, that level of performance is going to be slightly lower because of the fact we can't use speculative optimizations. Even if we use profile-guided optimization, it's going to raise it a bit, but we're still not going to get that same level of performance because we're not looking at the actual running code. So AOT is good, but it has limitations. There are definitely situations where you would use AOT. If you're using ephemeral microservices, things like what they call serverless computing, AWS Lambdas, very short-lived pieces of code that you just want to execute and then throw away, AOT makes perfect sense for that type of application. So what you do is you compile your code and then you run it as a simple service and everything works really well. Also works well if you're in a resource-constrained environment. If you're running a container that's got 2 vCores, then JIT compilation will have a significant impact on your overall performance level because 2 vCores, whilst you're doing warm-up, you're going to see one of those vCores doing nothing but compilation and one of the vCores doing application work. So effectively, you're going to see a 50% reduction in throughput whilst you're doing your warm-up, and you're going to have to do that warm-up at the same time. So AOT does make sense in those situations. Solution number 2, what about if we store information about JIT compilation? So this is what we have in terms of what we call ready now, and this is part of our Azure Platform Prime, the Zing JVM. So what we do here is we say, okay, let's run our application and let it warm up. So we take standard application, we don't do anything special with it. We start it up, run the workload in production, so we're getting exactly what is happening with our production systems and the realistic workload, and we do a training run. Let it warm up, get to that optimum level where we know we've got that number of transactions per second. At that point, we take a profile, and a profile, in this case, consists of 5 specific things. First is we have a list of all the currently loaded classes. The second thing we have is a list of all the currently initialized classes. And because the JVM uses lazy initialization, that could be a smaller, or it could be a subset of the loaded classes. But we need to know which ones are loaded, which ones are initialized. Then we keep a copy of all the profiling data that was collected whilst we were going to the C2 JIT compiled code. So where we've profiled the methods as they're being used, we take all of that profiling information, we write that to a file. Very importantly, where we've had to go through a de-optimization because we've made an assumption that proves to be wrong, we record that as well, so we don't make the same mistakes in the future. And then more recently what we do is we also keep a copy of all the compiled code, so that when we want to start the application up again, we can reuse that if it's possible. When we restart the application, we say, okay, we know what was happening when we took the profile. Let's reuse that information. Make sure we load immediately all the classes on that list. Initialize all the classes on that list. So we get to exactly the same point in terms of class loading initialization as when we took the profile. Then we'll load and potentially compile all of the methods that we know we need to compile because they were profiled in the previous run of the application. All of that will happen before we get to the main entry point. So when you hit main and you start your application, you're basically in a situation where you've got almost the same level of performance that you had when you took your profile. I say almost because there's certain things that the JVM mandates in terms of the specification that you have to do at startup, which means we can't quite get to that 100% level of performance we had before. It's about 97, 98%. 2 or 3 transactions, and then you'll be at the 100%. So if we look at our graph again, and we simplify that slightly, what we see is that without ready now, we go through this warm-up where we get compilation, and then we hit our steady state. If we look at what we get with ready now, it's going to look like this. So now we've got much closer to what we had with AOT. But remember, because we're still running on the JVM, we're still able to do JIT compilation, we're still able to do speculative optimizations, we can do de-optimizations if we want, then we get that same level of performance. However, there's always a catch, isn't there? And the catch is that there's this bit here where there's a period of time where you're not doing any application work. And that's because we do all this stuff before we get to main. So we have to load all the classes, initialize the classes, load compile code or compile code before we get to that point. What we have done is, so with using the code stashing, as we call it, so keeping a copy of the compiled code, that has been significantly reduced so that we don't have to do a lot of recompilation when you start your application. So it does start pretty fast now. One thing I will say is if you move your profile to a machine which has a different microarchitecture, so let's say you're using Sandy Bridge on one and Ivy Bridge on another, because they have different instruction sets potentially, then you will potentially still have to do that recompilation to avoid problems of not having the right instruction set available. But if you're still using the same platform, then it will get much better performance. Now, Project Leiden is part of OpenJDK. This has been around for a couple of years now, and it's a project which has the goal of improving startup and warm-up time. And they've been looking at three specific things. First of those is ahead-of-time class loading and linking. And this is JEP 483, which will be included in JDK 24, which I think is coming out next week. Yeah, probably next week, yeah. Now, what this does is essentially, if you know about application class data sharing, it's a similar idea to that. What it says is that when you start up your application, the JVM will load classes. When it loads classes, it creates data structures, which it has in memory. When you start up the application again, it goes through the same process of loading the class, creating that data structure in memory. So what application class data sharing and AOT class loading and linking does is say, okay, once you've loaded your classes, once you've initialized your classes, you can write those data structures that are in memory out to a file. When you want to start the JVM again, you can either load those memory data structures into memory again, or you could just memory map the file and get those data structures immediately. So it reduces the overhead of that initial part of the class loading and linking that occurs when the application starts. So that's quite a good idea. The second thing they're looking at, which hasn't been delivered yet, and there isn't even a JEP that's proposed for a particular version, is ahead-of-time method profiling. And this is the idea of caching the profiling data, which is used from a training run. When you start the application again, you reuse that profiling data to enable the JIT compiler to be more efficient. And then there's AOT code compilation, which is where you cache the compiled code from a training run, and then you reuse it when you start the application. Now, right now, they actually have this in three phases. So they do a training run to collect the information, then they have an assembly phase, and then they have a deployment run. Obviously, a lot of this will look familiar because it's exactly the same as what I just described in terms of what we do with Ready Now. It's just that OpenJDK has finally caught up with what we have done. Solution number three. What about if we decouple the JIT compiler? If we look at the structure of the JVM contains a number of different subsystems. So at the top, you've got the class loader subsystem, which does class loading, verification, initialization. In the middle, you've got your runtime data area, which contains information about methods. You've got your heap, you've got your stacks, you've got your native stacks and memory. And then at the bottom, you've got your execution engine. And the execution engine is where you've got the interpreter that generates these templates and then uses those to execute the bytecodes. You've got your JIT compilers, C1 and C2. You've got your garbage collector, and then you've got JNI and native method libraries on the right. So what we did was we looked at this and we said, okay, how can we improve things? And the easiest way to do this is to focus on JIT compilation, because that's where warm-up happens. Warm-up is all about compiling stuff as we run the application. So if we look at speculative optimizations again, what we can do is we can actually create a sort of compilation unit. And the compilation unit is a method plus a set of assumptions that we've used to compile that method. And taking the examples we had before, we could say, okay, for the monomorphic inlining, we guarantee there's only one getColor method, and we say that the value is not greater than 9, so we know that our method that we had for getValue, whatever, would work in terms of this compilation. So it's the method with a set of assumptions that have been compiled. What we find is obviously that JIT compilation has cost. We've already explored this. The fact that you're compiling code whilst the application is doing its work, You have to share the CPU and the memory resources so that you're degrading the amount of application work you can do whilst you're doing warm-up. The thing is that the better optimizations deliver better performance, but the more you try and optimize code, the more resources it requires. You need lots of CPU because it can often take a lot of processing to generate that compiled code. If you're running on a nice big beefy machine, if you've got 64 vCores, you've got 64 gigs of memory, it's not really going to be too much of a problem. If you're running on a small container where you've got 2 vCores and 2 gigs of memory, then trying to do heavy, hardcore optimizations is not really practical because you're going to use too much of the CPU resource, too much of the memory. You might even hit out of memory errors because you're taking so much of the memory that there isn't enough left to run the application code. So we often end up, when we're running in a sort of constrained environment, of having to compromise by saying, okay, let's not optimize as much because it doesn't require as much resources, but we don't get the best level of performance that we can potentially get. So let's look at this graph. Hopefully you can actually see something in this graph. There's a line there. So the top line is basically showing the throughput over time. And this is running on a 2 vCore container where we're just running OpenJDK, so hotspot compiler. Now you can see it warms up pretty quickly. So it's a fairly simple application. It warms up quickly and then we hit our steady state of optimized code. And if we look at the bottom graph, if you can see that, that's CPU load. So initially we're seeing a lot of CPU load because of the fact we're compiling our code at the same time as running the application. But that drops off when we get to the point where we've compiled all the methods and we can just use those methods as we run. Okay, so that's a standard sort of way that the code executes. And we did this with just a sample application running on a 2 vCore container. Now, if we take our own JIT compiler, so we have a different JIT compiler in terms of C2. We have one that's called Falcon. It's based on LLVM, which is another open source project. Now that does more heavy optimization. It tries to do different things in terms of optimizing code to give us better performance. So if you look at the far right-hand side of the graph, the blue line is higher than the red line. So ultimately, what we're getting is, in this case, about a 20% improvement in performance, throughput, which is great. So that's really good. So 20% more transactions per second, that could lead to a reduction in your cloud bill by maybe 10%. But if you look at the graph, it's much more variable and takes longer to get to that level of performance than we see with the orange line. So we're going through a slower warm-up, and they're also seeing lots of dips along the way. And those dips are de-optimizations. Similarly, when you look at the graph at the bottom, which is CPU utilization, we're seeing very heavy thrashing of the CPU for a lot longer, and then spikes where it has to do the recompilation, which is really, degrading the throughput that we get as we warm up. If this is a short-running microservice, this could be very detrimental to your performance. Longer running microservice, great. You can get to that level of performance, wonderful, all good. So how can we solve this? What we thought is, let's decouple the JIT compiler from the JVM. We're running in the cloud. We're running containers in the cloud. So rather than doing the JIT compilation locally in the JVM that's running the application, why not create a service, JIT compilation, JIT as a service, put it in the cloud, set it up with plenty of resources, plenty of CPU, plenty of memory, and then all the different JVMs that we're running, when they need to compile a method, they simply send a message over the network to the cloud native compiler saying, compile this method. It can then deal with it, because we send the method, we send the profiling information exactly the same way as you would to the JIT compiler locally, you just send it across the network. Now that's not an issue in terms of network bandwidth, because if you look at methods and profiling data, they tend to be quite small. So you're not sending gigabytes of data across the network. Network latency, so long as you locate your JIT compiler as a service local to your VMs, then latency is not going to be an issue either. You wouldn't want to run your JIT compiler in Singapore and your application in San Francisco. That wouldn't make sense, but run them in the same local instance. This is great, you see, because now we can do the compilation remotely. That means that we can spend longer working on the compilation. We can also reuse that compilation. You start up multiple instances of a service. The first service that starts up needs to compile method A. It gets compiled. When you start up the same method, start up the same service to address load, then when it says compile method A, as long as we can match that against what we've got in our cache, we can then return it straight away. So we're optimizing for reusing compiled code. So if we look at our graph again, so this is the one we saw before. With Falcon, we've got a much more spiky graph, a lot more use of CPU utilization. Overlay that with what we get using Cloud Native Compiler, and if I drop out the blue one to make it more obvious, what we see now is the green line starts up at the same speed as we get with Hotspot. So we get very, very quick warm-up, but we're getting to that optimum level of performance very quickly. So almost as fast as we get with Hotspot, but we're getting 20% more throughput. Similarly, if we look at the CPU utilization, because we're not doing it locally, we're in a 2 vCore container, both vCores can almost immediately be used for application code. So this is a big win in terms of performance and warm-up overall addressing. But of course you could say, well, isn't this just shifting the cost? We're shifting the cost from the local JVM to a centralized service. But yes, we can take advantage of the fact that it's centralized. We can do it in a more efficient place. We can reuse our code when we have the ability to do that. So we're not necessarily compiling things every time. But the other thing that we're working on now is the idea that when a service starts up and it says compile this method, we compile it and we send it back. So we do it as quickly as we can based on that profiling information, send it back. What we'll then do is if we're not busy in our Cloud Native Compiler, we'll start working on that method again, applying even more heavy optimization. And we can do much more kind of grinding of the CPU because it's not affecting the throughput of that service. So the next time that an application asks for that particular method, we've got an even more heavily optimized version available, or we could even preempt that and say, send a message back to the service and say, I've now got a better version of this method, do you want it? And send it back across the network. So there's a lot more optimization possibilities that we can do in terms of using it as a centralized service. We can cache the code, we can do more heavy optimizations on it. And like I say, the fact that we can match a particular set of assumptions means that we can keep multiple compiled versions of the same method, but using a different set of assumptions. When we match that against what the service is asking for, so long as it matches, we send it straight back. If it doesn't match, then we can compile it based on a different set of assumptions and generate a different compiled result for the same method. And that, again, gives us flexibility and better performance. Solution 4, what about if we combine solutions 2 and 3? So what we did here is we created a thing called the Ready Now Orchestrator. And essentially what that does is it says for the Ready Now profiles, rather than keeping them locally, we can keep them in effectively an S3 bucket or a remote file system. And that way, when a service starts up, we can provide it with whatever is the latest and greatest Ready Now profile. We don't have to bake the profile into the Docker image. We can just remotely access it, bring down that Ready Now image, Ready Now profile. Then we can use our JIT compiler. We can use the Cloud Native Compiler in conjunction with that. And that gives us both the ability to understand what classes and everything we need to compile, plus what methods to compile, but compiling them remotely rather than locally. And that has proved to be very good for some of our very large customers. Solution number 5, what about if we save the whole application state? Right, so we've talked about the idea of compilation data, JIT compilation, because that's what we see in terms of Warmup. But what about if we do something even more than that? Now, on Linux, there is a thing called Coordinated Resume in User Space, or CRYU, as some people try to refer to it as a word. Linux project, and essentially the idea of this is that if you think about when you're using your laptop, you're working on some files, doing a word processing document, you've got some tabs open on your browser, you need to move to a different desk, you close your laptop, and everything is frozen. You move to a different desk, you open your laptop, everything is there as it was before. Why not do that with an application? So, on a server, so this is what cryo is about. You essentially freeze a running application. And the way you freeze it is to take all the information about the state of that application and write it out into user space. So it gets put in the file system as a file. And what it's essentially doing is, if you look at the diagram at the bottom there, you can think of it like in a time-sharing operating system, when you want to swap between processes, you need to record the state of that process in order to swap it out. So you record the program counter, you record your registers, you record your stack and everything, you write that out into memory, and then you swap in another process. This is essentially the same thing, but rather than storing in memory, we write it out to a file system so that you can reuse it at a much later time, even after the machine has been rebooted. Potentially, you can even move it to a different machine and restart the same application on a different machine. So this sounds really good. But what we said was, okay, that works really well, and the JVM is just a process. So if we could use cryo, we could simply use cryo with the JVM, and we could store the state of the JVM and then restore it at some later point. But that is not going to really work terribly reliably. If you have things like a JDBC connection, if you have a network connection, then if you store the state of that and then you try and restore it an hour later, that JDBC connection may not exist anymore, the network connection's timed out, all sorts of problems with restarting your application reliably. So what we do now is we take cryo as the layer underneath to store the state of the JVM. But we make the Java application aware that it is being checkpointed. So our application is running along quite happily, and then we say to the application, right, we're about to make a checkpoint, do whatever you need to do to prepare for that checkpoint. We then write all that information out, and then sometime later, we make the application aware that it is being restored. So it can then do various things to restore its state reliably based on what it did when it was checkpointed. And then the application continues running. What we do is we actually enforce more restrictions than cryo does. So we say that you cannot do a checkpoint if you have any open files or sockets. So all open files, all open sockets must be closed before you do a checkpoint. That way we can reliably restart the application, and then you have to re-establish those connections when it gets restored. If you try to do it with an open socket or open file, the checkpoint will be aborted. How we do this is using a very simple API. Any class which needs to be aware that it's going to be checkpointed and then restored, so something that has a JDBC connection, for example, you implement the resource interface. That resource interface has two methods called before checkpoint and after restore. You'll never guess where those methods are called. So the before checkpoint is called before we do a checkpoint. So what will happen is you'll say, right, we're about to do a checkpoint. I have a JDBC connection open. I will close that JDBC connection. When we do a restore, we'll go after restore, that method gets called, we go, right, we need to restore our JDBC connection, open that up, check everything, maybe do any verification or whatever, and then the application starts running. Same with files, same with network connections. With a file, for example, you can do something like saying, okay, when you close the file, do a checksum of the file. When you restore, you can then open the file again, but you can also do a checksum and compare to see if the file has changed. If it's changed, you may need to reread it, to reprocess, whatever, but it gives you that ability to do that. So you have the interface resource with the two methods you implement. Then you have the idea of a context. So you implement those two methods, but for all those classes, what you need to do is register them with the JVM so that it knows to call those methods. So you use the register method in the context to register that as a resource. You get the context from, there's a global context, you can create your own if you want, but most people just use the global context, static method that you can call to get the context, and then register your resources, and it will all work quite happily. Nice thing about this is you have your list of things that require after the resources that you need to use in your context. What happens is that the order that you register those resources is the order in which the before checkpoint methods will be called. So you can define the right order for your application. So if one class needs to be deal with things before another class, then you just register it before that other class. So it will call them in the order that you register them. On the way back after restore, it reverses the order. So you come like down the stack and then you come back up through on the way out. So there's a defined order and it allows you to do things in a specific sequence. Does it work? The answer is yes. So here's some proof of concepts that we did. We've created a version of OpenJDK. You can download it from our website. It's free. You can experiment with it. And what we did is we compared doing a checkpoint and restore to some standard application type frameworks. So Spring Boot, we did a Spring Boot application. I think it was probably the pet store type thing. And running it on a particular machine, don't know what it was, but a particular machine, time to first transaction was basically 4 seconds. To start up the whole stack and get everything running, 4 seconds. Doing a checkpoint and then doing a restore, the time to first transaction, 38 milliseconds. So that's 2 orders of magnitude faster. You're literally instantly on, and you've got all your state associated with your application. Everything that was in the heap, everything you processed before, all there, ready to go. So there's none of this having to redo that. Same with Micronaut, that was a second getting to first transaction reduced to 46 milliseconds. Quarkus, again, about a second down to 33 milliseconds. And a less representative XML transform, 4.3 seconds down to 53 milliseconds. But same kind of idea, 2 orders of magnitude faster. So just to summarize, basically, solving the JVM warm-up problem. No one solution is going to fit everything. So what we talked about here is different solutions for different types of situations. If you're looking for, AWS Lambdas, serverless computing, then AOT, Graal VM or Graal native image type of thing is a very good approach. But if you're looking for longer running applications where performance is more of a benefit to you, then using JIT compiled code is good. Using our Prime JVM gives you even better performance because you got that. Plus the idea of maybe shifting the compilation into the cloud native compiler to eliminate the load on the system that's actually doing the work, various things like that. Ready Now Orchestrator, combining both a profile and cloud native compiler. And then Crack, which we just talked about, is being able to restart your application from a known point. Project Leiden, also looking at all these sorts of approaches, and we'll probably come up with some other ideas in the standard JDK in the future. So with that, I don't know if anybody's got any more questions. I know we had a few questions whilst we were talking, but if anybody's got any questions, but otherwise, thank you. Question?
I'm finding myself wondering, how does this work in a continuous integration continuous development environment where my classes change every single time I deploy?
Yes. Yeah, so that always is going to be a struggle. So what we've definitely worked with customers who've done that kind of thing. So what they can do is they can actually integrate some of that training run into their CI/CD pipeline, so that when you generate a new set of classes, you would then have to generate a new training run for it. But it isn't as straightforward as, when you're doing CI/CD and very frequent changes, then this becomes more of a challenge simply because you have to do a new training run because you can't reuse the profiles or even the compiled code, because if you change it, then it's not going to work. So yes, that is a situation where this becomes more of a challenge.
I guess kind of related, the cloud native compilation, how does it know that the class hasn't changed?
Right, so we can do that because we can basically provide a fingerprint, if you like, of the class. So we know when we can, essentially what we're doing is a checksum of the class bytecodes. So if it changes, we know that it's changed. And then, oh yes, yeah, that definitely works in that situation, yeah. Yeah, we can deal with that.
Would you have a run where you deploy a patient is running in prod, and then you recognize that it's, I guess that was my other question, is there an easy way to recognize that it's warmed up to the point where it's not warming up anymore? And you can take us half as well.
That's more of a thing that depends on your application. So you as a DevOps or a developer would need to establish what your level is that you're looking for or observing in terms of that warmed up. So you have to decide when it's warm. Sorry?
Would that be featured in the VM itself? Say, hey,
Well, we can do so much in terms of we can give you reporting in terms of how many methods or which methods have been compiled. But knowing whether that means all of the ones that are frequently used have been compiled is not something we can easily analyze. So it really comes down to you have to look at the performance of your application to decide when you think it's warmed up, unfortunately.
I definitely see a case where this is not serverless, right? If you have some sort of upscaling situation where you can scale something upscale throughout the week, perhaps after every deployment you have that first half a day, and then you take the snapshot right after the
Yes, and I mean, with the Ready Now orchestrator, that's one of the things we do is you can actually store multiple profiles for the same application. So you can have a profile which is a Monday morning profile, and you can have a Friday afternoon profile, which are potentially different. And so when you need to restart the service on a Monday morning, you use that profile versus the Friday afternoon profile when you start it on a Friday afternoon. So you can definitely do that kind of thing.